Okay, memoization. So exercise 3.27 is the one that asks you to draw an environment diagram for Fibonacci numbers. And it's a big pain in the neck. If you actually did it, the diagram you got was long and complicated. But let's look at fib.scum. So what we have up here, the first procedure, fib, is the simplest, most straightforward possible way to implement Fibonacci numbers. Namely, numbers 0 and 1 are 0 and 1. So if n is less than 2, return n. And otherwise, return the sum of fib of n plus 1, n minus 1, sorry, and fib of n minus 2. Because that's the definition of Fibonacci numbers, right? Each one is the sum of the two that came before it. So if we actually do this, we can take, fib of 6, fib of 15, fib of 20. See, there was a little bit of a pause there. Oops. Fib of 25 has quite a noticeable pause. Fib of 30 is already way too slow to be comfortable. So as you know, for this particular problem, there's an iterative method of doing Fibonacci numbers that runs in linear time. But I want to look, while this thing is taking its time. There we go. We finally got an answer. I want to look at this implementation. So I'm going to say fast fib of 30. What? Uh-oh. Did I make a mistake here? Fast fib 30. Huh. Oh, wrong get. Bleh. Let's start again. I wanted to use the table that the two-dimensional table that we built in. And I had this one-dimensional table in the way. So let's load fib. And now I can say fast fib 30. And I get the same answer, but I get it instantly. Takes a little while. But not exponential time. It's only quadratic time. Here. Oops. Oh, I see. Control O, that's what I mean. Control N, Control O. There we go. That's how big it is. So how does this code work? It works by a technique called memoization. Which is a little bit of a tricky word. So I'll write it down. Doesn't have an R in it. It's just memoization. Although it's related to memorization, because what we do is every time we compute a value for this function, we remember it. And here's how that works. FastFib says, if n is less than 2, return n, same as before. And now, let me do a get. This is the kind of get that has two keys. So it's the situation I was telling you about before, where one of the keys is a number. So the first key is the word fib. That's sort of the operator that we're doing. Only instead of a data type, the other key is the number that we want fib of. So we look to see if the number is already in the table. If so, just return it. If not, then I call fastFib twice, add the results, put it into the table, and then return that value from the table. I could have used the let to put the sum in the variable result and return that, but it was just as easy to get the result. So if we look at the table, what we find is I can say get fib 100, and it's stored in the table. And I can also say get fib 99, which is a slightly smaller number, because all the intermediate results are stored in the table. Because the reason the ordinary fib takes exponential time is that it's doing redundant work. Right? Does everybody understand that? Let's draw a picture. I want fib of 100. In order to do that, I need 99 and 98. Well, for 99, I need 98, 97, 97, 96, 97, 96, 96, 95, 96, 95, 97, 96. Okay, so we're calling fib of 96. 1, 2, 3, 4, 5. Whoops, nope. Lost what I was doing. So just 4 times for fib of 96, because it's 4 down from 100, I guess. So by the time we get to fib of 3, we're calling it a bazillion times, right? Namely 2 to the 100th times, more or less. And using this table for memoization avoids that repeated calculation. So how long does this take, do you think? Theta of what? Theta of n? Theta of n squared, maybe? Okay, you might think, yeah. Good question. Well, now you know how tables are implemented. You tell me, is our table O(n) lookup time? No, the table that we gave you, the get and put, is that table. It's one of those. So you might well think that the answer is theta of n squared, because we're making n calls to fib, and each one does a lookup that takes theta of n time. As it turns out, we're lucky about this because entries are added to the table at the beginning. So when I'm trying to compute fib of 100, it just so happens that fib 99 and fib 98 are at the front of the table. So it takes a constant amount of time each time to do the 2 lookups that we have to do. And therefore, the whole computation is theta of n. Provided that the numbers are smaller than plus or minus, well, plus, I guess, 2 billion. When the numbers get bigger than that, the computation, the adding for each number takes time proportional to essentially the number of digits in the number, which is log n. So the running time for very large numbers will be n log n. Okay? But that's, knowing more than you want to know about how numbers are implemented. Basically, as far as the table business is concerned, we're just really, really lucky about the order of things in the table. And so each lookup takes a constant time instead of theta n time. If we put things in the table in random order, then it would take theta n time to do each lookup. OK, so that's memoization. Now, we did this memoization using a particular kind of table structure that is built into our initialization file for scheme for this class. You don't have to use this particular data structure. So, you know, when you're finished with this class, you may never again see exactly this kind of table. But you will, I promise, see memoization. And it's going to really save your life. It's going to take problems that would otherwise use exponential time and turn them into linear time, or maybe at worst quadratic time programs. So really, really, really important technique for optimization that's based on, let me remind you, the ability to mutate a data structure. Because what makes memoization work is those set cars in the put procedure. Okay. Oh, which reminds me, is fastfib a functional program? Let's take a vote. Who says yes? Who says no? Oh, come on. I think like hardly anybody voted. Here's a sideways thumb. Yeah, is that a hand up or no? Okay. No, okay. It's a tricky question. It's a really complicated question. The argument for yes, which is a very good argument, is that if you pay no attention to its implementation, it is absolutely functional. Every time you call fastfib with the same arguments, you get the same return value. The argument for not being functional is that if you look down under the abstraction barrier, you can see that things are being done by mutation. So that makes it not functional. The counter-argument against that argument is every single thing you do on a computer, if you look closely enough, involves mutation. So that kind of licenses us not to look below the abstraction barrier if the program actually is functional in its behavior.